Hi everyone, welcome and thank you for joining me today. My name is Andy Yoon and I'm a Principal Solutions Engineer with SentryOne. And I'm really excited and honored to be presenting for you all today for SQL Bits 2020. I really wish I could be there with you all in person, of course, but I'm still glad that we're able to get together and do this virtually. So without further ado, I am pleased to present to you Advanced Plan Explorer usage for tuning your execution plans. So here's a little bit of biographical information about me. I've been working with SQL Server for quite a long time, and I've actually been using Plan Explorer for quite a number of years of that career as well. I'm also fairly active in the SQL Server community. Up there you'll see my contact information, my Twitter handle, my email address, my blog, and I love to engage, I love to chat, I love to talk shop. So please never hesitate to reach out to me. But otherwise, this is all kind of fluff, and we can now move on. So, before we begin, I do need to address the elephant in the room. I work for SentryOne. Plan Explorer is also made by SentryOne. However, I want to reassure everyone here that this will not be a vendor, sales, or marketing presentation. I've actually developed this as a community session. I want to teach you all about using Plan Explorer. I don't want to sell you on using Plan Explorer. So my promise from here on out is that you're not going to hear anything marketing or sales related or anything else like that. All we're going to be doing is talking about the free Plan Explorer tool from here on out. Now, I also want you to understand that today's goal is to showcase advanced features and functionality that are often overlooked in Plan Explorer. This is not a true query tuning session in that I'm not going to be teaching you exactly how to fix specific anti-patterns. We're going to be looking at common anti-patterns within Plan Explorer so that you can discover that these things are happening and different details about them. Okay? And Plan Explorer is all about increasing your speed and productivity while you are doing performance tuning. So this is why I really want to teach you all about, leveraging some of the more advanced stuff about Plan Explorer so that we can increase that speed of yours. This presentation is going to be mostly demo, and I'm not going to be covering the basics. I want to be very clear about that. There's a reason why advanced is in the title of this presentation. On the other hand, if in case you did wander into this particular presentation and maybe you've never heard of Plan Explorer, understand that it is a completely free tool from SentryOne, and that here on this particular slide is a full list of different resources that you can leverage in order to learn the basics and intermediates of Plan Explorer. Of course, I don't necessarily expect you to write all this stuff down, but if nothing else, write down that GitHub or just take a quick screen cap of that. All of my slides and my demos, the PE session files that I'm going to be using, are all up there in a dedicated repository. All right, so let's get started. So first of all, I want to kind of set the stage and put us into a mindset of Management Studio versus Plan Explorer. Why should I be using one over the other, and when should I be using one or the other? And to do that, I really like this particular quote. I think that there are two steps in the evolution of a query: ensuring correct results and performance optimization. This quote is by Aaron Bertrand, who used to be the product owner of Plan Explorer. Now, I really like this because the thing is, Management Studio is all about making sure are my queries returning back exactly what they're supposed to be, the 110 rows that have this and this and this data and so on and so forth. But once I've locked that down, think about using Plan Explorer not to just look at the execution plans, but to use it as a development environment to do your query tuning in. That's what I really am hoping to shift your mindset about using Plan Explorer and to use it as an environment for performance optimization. So to accomplish all of this, the first thing I want to talk about is customizing your UI. So these days, especially with most of us stuck at home working, is that maybe all we got to do is just bring home a single laptop. So when I'm working in a single screen like this, Plan Explorer is going to be kind of cramped because frankly, Plan Explorer is an extremely information dense tool. There's all sorts of information buried in numerous different tabs, columns, hidden columns, so on and so forth. So when I'm just looking at one single either execution plan or PE session file, I'm going to have to move windows around. I'm going to have to resize them in order to really best leverage things. So right now, for example, we're looking at the results tab, the plan diagram, and index analysis. But if I want to expand index analysis so I can see the statistics histogram, I'm going to essentially have to shrink the plan diagram. So everything is a little bit of a sacrifice, a little bit of a trade-off. But here's the thing. Many of us, after being stuck at home and realizing that, oh, this is going to last more than a couple of weeks, went out and invested in some more hardware. I went out and bought a second monitor. And now that allows me to drag and drop various tabs and windows from Plan Explorer onto a second monitor, as you can see here. So this is what everything kind of looks like right now. The left-hand side is one monitor, the right-hand side is the other monitor. And in this example, I've dragged the plan diagram over into its own dedicated monitor. So now I can see the entire plan diagram in its full glory. This variation, I happen to have the query columns and index analysis all stuck on one monitor, while on the other monitor I have the plan XML, plan diagram, plan tree, and the statements results all up in the second monitor. So you see here, I have all this other information right at my fingertips. Now I don't have to juggle nearly as much. I can take advantage of that extra real estate that I get from having that second monitor. So that's it for the slides. Let's dive into Plan Explorer itself for the remainder of this presentation and all the other awesome demo. So next I'd like to talk to you a little bit about parallelism. So parallelism is something that we have to contend with on a regular basis. Sometimes we have good parallelism where we're distributing a large workload amongst many threads to lessen the overall time of execution. Other times we have bad parallelism, whether it takes the form of unbalanced distribution of records amongst worker threads, or queries that are so cheap and fast that really the extra slight overhead of going parallel actually winds up hurting us. So to that end, I want to show you how you can figure all that type of stuff out within Plan Explorer. So first of all, I'm going to go up to the Statements tab up here at the top, and then I'm actually going to right-click and go to Column Chooser and add in something called Parallelism Operations. So let me describe the couple of data points that I will be focusing on. First, degree of parallelism is pretty straightforward. It tells you how many threads a given statement wound up using, whether it be 1 or, in this case, 4. So this statement obviously went parallel. And then parallel operations tells me how many operations in the execution plan actually went parallel, such as a scan, for example. Whereas parallelism operations tells me how many physical operators that are related to controlling of parallelism, whether it be like a gathering of streams, for example. So let me use our filter functionality, and I'm going to go up to custom and select 3 here, and then I'll select this guy. And then let's come down to the bottom inside top operations. Let me resort top operations down here, and I'm going to scroll down to the bottom. I need to reselect this guy. There we go. That now updated. Okay, so now in this particular statement that I've selected, remember that there were 3 parallelism operations. That's actually what I chose to focus on. And in this case, there's a gather streams and 2 repartition stream operations. Now if I scroll further over to the right, here are all of the other operators that went parallel. So this way I can see whether a given scan was able to go parallel or not, because sometimes in execution plans, it's not that the entire execution plan goes parallel. Some portions of it can go parallel, and then you can go back serial, and then you can actually go parallel again. It can jump back and forth. So sometimes it's very important to see that extra level of detail. Now, in addition to that, there's also the key question of whether we had parallelism distribution or unbalanced parallelism, I should say. So you should really be looking at how evenly distributed was your workload amongst each of the different threads. And to do that, we're going to go to the very similar but different Plan Tree tab down here. And in the Plan Tree tab, I happen to be able to show you the different threads that were in play, 0 through 4, because the 0 thread is essentially the main or control thread, and then we wound up distributing our workload to the others. So for example, these couple of statements went parallel, and they distributed around just over 700,000 records to each of the different threads. And that's pretty good, well-balanced parallelism. Over here is an example of slightly unbalanced parallelism where thread 2 and 3 got about 700,000 records, whereas thread 1 got a little bit less and thread 4 got a little bit more. This is still pretty close to one another, so I probably wouldn't be too worried about this. However, let's pretend for a moment thread 4 only got 9,000 records. Then I'd be much more concerned about this. Or what if it got 900 trillion records? Then I would definitely be very concerned about this. Frankly, what I usually see is that one of the threads in play usually gets a whole heck of a lot more than all of the others, as opposed to all but one gets, a far less than the others. I usually see the first pattern more often than the second pattern, but again, both of them can occur. And if I see this, then I'm going to want to look into the underlying statistics that are in play. Now, the other question you should be asking yourself is, should I be going parallel? Because many of us have fast running high volume queries that wind up going parallel because we didn't properly adjust cost threshold for parallelism. And remember that cost threshold for parallelism defaults to 5, but we should really look to at least a starting value of 50 and then adjust from there according to our workload to best determine whether we want those very fast queries to actually go parallel or they should not bother going parallel. So to help do that, I'm going to do a couple of things up in the Statements tab. First of all, a quick tip. We happen to have a filter applied here, and if there's ever a time where you've applied a filter, you've been working with the particular data grid or whatever. Fuck! Okay, first of all, a quick tip. If you're ever looking at any of our different data grids and you're wondering, wait a minute, why are there different records here, or there's something I expect to see but it's missing, always visually double check the bottom of the data grid and see if you happen to have a filter applied, right? Because I can't tell you the number of times I've totally forgotten that I applied a filter. Maybe I applied it in the last time I was working here. And then, I start doing some other kind of work and I'm like, where did my data go? There should be more stuff here. So I'm going to wipe this out here. And then I'm going to scroll down to a different example that I kind of want to talk about as far as fast parallelism. So here we go. I happen to have a statement within a store procedure that goes parallel. And the key question is, do I really want it going parallel? If I look at the distribution real fast of the data, it's moderately unbalanced here. But really what I want to focus on is another optional column that's inside top operations. Estimated total subtree cost. So what I'm actually going to do is sort by the estimated subtree cost percentage column here in order to find the operator that has the highest estimated total subtree cost. And that essentially corresponds with the final operator that's inside the execution plan. In this case, it happened to be a parallelism of gathering streams. Let me zoom back out just to show this to you in the plan diagram. There we go. So the parallelism gathering streams happen right before that controller select into operator essentially. So our estimated total subtree cost was about almost 36 units. Now this is a perfect example where it falls between the default of 5 versus the recommended starting point of 50 that a lot of folks will recommend, myself included, as a starting point and then tune from there. And this is an intentional example of a query that I really don't want to really be going parallel because it's something that my workload executes in tremendously high volume. So there's actually additional overhead from going parallel. I don't get a whole heck of a lot of benefit from this. So make sure that you double check top operations and that estimated total subtree cost value. Of course, you could mouse over the select into and derive that value from there inside the tooltip, but I also wanted to show you that it was also available to you inside top operations. Okay, so let's move on to our next demo. Oh, by the way, so, we've done a little bit of filtering, we've done some sorting. Let's pretend I've, sorted some different columns here and that sort of thing. I just clicked on duration, for example. Well, one thing that you can do is I can right-click up here on the statement, and then one of the options I'll have is reset sorting. So if you've ever messed around with your result sets and you want to go back to the default sort, which is the order that all these statements actually occurred in, make use of the reset sorting functionality right here. Okay. So now I also want to find a specific piece of code here. So what I'm also going to do is I'm going to click on the tree here, and notice I have a couple of different options. Expand all and collapse all. Because I've executed this inside Plan Explorer, I happen to have the full call stack, so I have the hierarchy here. So I want to get down to a specific piece of code. So I'm actually going to right click and collapse all, and then expand this one level. And I actually want to go find a specific store procedure for this next demo. Okay, so I happen to have this store procedure and then this store procedure here. It's called spget sales summary by state. I'm going to pull this up just a little bit so that way we can get some more screen real estate. I'll select the first select statement in here so that we get a nice little plan diagram. So first of all, let me actually show you what this code is all about. So this is a store procedure that essentially is just doing a query with a bunch of different joins where I'm going to say where the customer state is equal to a given variable value. And if you look in here in the call stack, you can see that in my first execution, I'm declaring my state to be Alaska, and then I'm resetting it to Illinois thereafter. So I'm going to execute it for all my different customers and their sales history information for one state, and then re-execute it for yet another state. This is essentially what's going on here. So if we look at the corresponding performance metrics here of the two different executions, we have a little bit of a problem. Duration 40, duration 4,200. That's a heck of a difference here for running the same chunk of code. The only difference really being is the two different parameters here. And some of you may be thinking ahead, thinking, oh, I know exactly what's going on here. This is a classic case of parameter sniffing, and you'd be right if you were thinking that. So this is one of the easy ways to kind of see what's going on, but I want to show you some of the other details or other ways to kind of look at this. Maybe you don't have that first execution to get a better sense of whether you have a parameter sniffing issue or not. So the traditional methodology is to look between estimated and actual. But in this particular case, because I'm doing aggregations here, the overall output, this doesn't help me here. So that's not something that really is all that effective in this particular case. But in Plan Explorer, I can do something kind of cool by looking at the different visuals here, right? So, but I have this button up here at the top called Show Estimated Plan. This is one of those buttons I always kind of overlooked and never really thought about it. But what it does is that when I'm looking at an actual plan, which is what we're looking at right now, I can quickly click on this button and it'll change things up for me. So I'm going to flip it back and I'm going to flip it forward. And there's actually very little change in this particular execution plan. This is the first execution for Alaska. Now, if I go to the second statement down here and I were to flip back and forth, there's a much more dramatic difference. You see the line bar thicknesses are now changing. I can just quickly see from a quick visual perspective that, hey, wait a minute, my estimates for my actuals, they're a little bit off here. There's something different that's going on. And of course, I can drill into the details if I go into top operations. And this is where I can see for a given operator the estimated versus actual rows and the estimated versus actual executions. And I can see how they dramatically differ here. But sometimes just doing that quick visual check, because again, we were all about speed here. Just quickly flipping that little button to show estimated plan can really help you out, speed things up to just quickly see, is this something that, that is causing you problems or not? Okay, so you're probably guessing or thinking to yourself that there's some kind of distribution of data here, some kind of data skew that's going on, and the answer is yes. And if I was in Management Studio, typically I would just be doing like a select count with a group by against customers and states just to see the number of different customers by state or doing that kind of analysis. But here's the thing. I don't necessarily need to look at the underlying data. All I really need to look at are the stats because that's all the query optimizer is looking at is the statistics. And because I executed this code in Plan Explorer, I can do that straight away in index analysis. So let me resize this now. And then I'm also going to select the customer operator in here. There it is, right up here at the top. And then I do need to select the state But now I can see the statistics histogram here, and there's a whole bunch of really awesome information here. So first of all, let's just zoom in and take a look at the stats histogram in of itself. In the United States, there are only 50 states, so I only have 50 discrete values here. And I have these orange bars here that are giving me a good indication of how much data there is on a per state basis. Notice that Alaska actually has next to nothing, whereas Illinois has a whole heck of a lot of data here. This blue bar that you happen to see is a visualization of the range that is being selected by your particular query. So you can quickly visually see that. Let me mouse over this to look at the tooltip. And now you can see some additional information. We see the range rows, the equality rows for the range key of Illinois here. And then we see the estimated and actual that was used here. Where did the estimated and actual come from? Well, if I scroll further on over to the left, notice that I have this really awesome parameters tab here in index analysis. And I see that the execution plan was compiled with a state value of Alaska that only gave me 76 rows. And our estimated operator here was going to be a seek, but really we wanted a scan because we have a total of 198,000 records here. So this wound up being a range scan type of operation because we had to consume a heck of a lot more information. So this is a really cool way to see that extra layer of information. By the way, I can compare and contrast this with the first execution. Let's take a look at the query history histogram on that guy here. So let me find my customer operator here. And and then I have to select the state. And in this case, let me actually grab the highlight as well. And in this case, we actually see that, yeah, here's the estimated rows of 76 records according to the histogram. In the end, we wound up pulling in 101 records. But this is a heck of a lot closer to our estimation of what we want to be seeing, right? So this is a good thing. So what I'd like to do is kind of point out a few other characteristics of index analysis, things that are kind of overlooked. For me, one of the things that I always overlooked were the visible column checkboxes. These are things that were just always kind of there and I always kind of glossed over them and I never really paid attention to them. But this will actually show or hide the different columns that are part of the given table that we're looking at. In this case, this customer table. Indexed and used in query are the only two columns that are, or only two options that are selected. So we only see customer ID and state. However, I'm going to select other. And now we will see there are a heck of a lot of other columns that are available to me in the customer table. And this could be very important if I'm deciding to use index analysis for playing around with different non-clustered indexes and creating hypothetical non-clustered indexes. Because there may be a non-clustered index that is not necessarily used in the query or has columns that are used in the query, but that I know that I may still want to include them nonetheless. So, for example, hey, by coincidence, this particular query here has a missing index recommendation. So I'm going to open this up a bit so that we can fully see this guy here. And in this case, this simple missing index I'll do this like this. In this case, this simple missing index recommendation just wants the state value. And it's really just a simple single column key. But you know what? Maybe I know that there's a lot of code here in my workload, not necessarily this query, where I'm going to need the first name and the last name and first visit, right? So what I'm going to do instead to create this missing index is I'm going to click on these guys, and I'm going to add these as included columns. And this is something that's definitely going to help me out here. By the way, one other thing I forgot to mention, we have this missing index recommendation here. If I scroll up to the top here, this is the missing index recommendation column. Notice that we had that summary value of 1 here. So had I pre-sorted the results set just to look for any statements that had missing index recommendations, I'd immediately been brought to this. So this is a great way to see that I had some low-hanging fruit here. So Remember that I can always, hit the S button in order to script the index, and maybe I'm living dangerously and I'm going to execute this in production. But also keep in mind that sometimes an index is not the reason for, an issue that you may be having. You may need to just update statistics instead. And that's one reason why we show you the last time stats were updated. And that's where this particular value comes into play. Also, you may have stats that are out of date on the column level as opposed to the index level. So we show you that information here. While I'm here, I also want to point out a few other columns that I believe are often overlooked. So we have the density value here, so that way I can get a better sense of the cardinality of each of the different underlying data for each of the within each of the different columns. Average length, so maybe I happen to have different strings or data types of different lengths here. Estimated size, but what I really find most useful is the predicate here. So this is something that can help me make index decisions when I can see which columns are being joined against and or which columns are being seeked or scanned against. Maybe I have a range or a quality or inequality type operator that's occurring against one of these different columns here. So frankly, it's the predicate column that I find the most interesting, but I also wanted to point out there's these other data points that you should take a moment and take a quick glance at. Okay. Now, let's live dangerously and let's take that missing index recommendation. I'm actually going to apply it here, so I'll just create missing index 1. We're going to execute that right there. And then I'm actually going to go grab the underlying code. So I'll just do a copy statement to command text. So it's here already. And then I can grab this next guy here. Oh, whoops, I want the procedure down here. So I'll just copy the cell, execute that. And then I'll do this once again for IL. Okay, so let's get actual plan right here. And let's see if this actually helps solve our problem or not. So in this case, no, this missing index recommendation did not at all because the underlying problem is really parameter sniffing. Now, more interesting, so, I could apply more missing index recommendations because there's still a different missing index recommendation that's out there. But this is a case where missing index recommendations don't magically fix the problem, make things go away. This is one of my rants or, kind of pet peeves about, folks who are, trying to learn query tuning or, don't really understand SQL Server. Oh, just apply all of the missing index recommendations because I've been in companies where people don't understand SQL Server and they say, we just apply all missing index recommendations. Oh, that's such a terrible idea for so many different reasons. And this is a simple example of applying missing index recommendations are not going to help magically fix your query. There's other underlying problems. In this case, parameter sniffing. Okay, so let's look at a slightly different type of example here. So I'm going to scroll on up to go find this particular statement here. Now, if you look in the statements summary tab, we happen to have key lookups, right? And in this case, this is a non-zero value. So I had a couple of key lookups that occurred here. And to refresh your memory, a key lookup is a operation where we made use of an existing non-clustered index, but then we had to go back to the clustered index in order to get an additional bit of information. And here it is in the plan diagram where I'm doing a key lookup against the inventory table right here after we seeked on this inventory VIN number non-clustered index right here. So I'm going to select this guy here, and then let's take a closer look at the underlying statistics histogram because I want to show you something else that's pretty cool that we've introduced inside the stats histogram. So inside SQL Server, there's something called the tipping point, where depending on the cardinality and the range and the underlying values in the statistics histogram, SQL Server will choose to either use the non-clustered index that does not fully cover the query and then do an additional key lookup operation, or it'll forego use of the non-clustered index entirely and do a full table scan instead. And that threshold where that happens is known as the tipping point. There's a couple of different rules around that, but what's really cool is that we can help you visualize that now in the statistics histogram here. So I've selected the index seek operator. I'm going to mouse over the where it is exactly here in the histogram itself. And notice that, okay, so we have the blue here. This is where we're actually, the VIN number that we were seeking against. Estimated number values 1, average range rows 1, because we're just looking after one specific VIN number. So that's to be expected. But this new data point down here at the bottom, the tipping point range, and that is materialized or visually materialized with this pink horizontal bar here. So what we're attempting to show you is the range of distinct values that you would need to be grabbing. And if you fall above that, that's when SQL Server is pretty much probably going to tip over and choose to use a full table scan instead of a seek and a key lookup operation here. So if I scroll further to the left here, notice the range scale over here on the left-hand side, so you can see approximately where everything is. Also, whoops, one other thing I wanted to point out, sorry about that, is the dotted lines for estimated rows and actual rows. Notice that, there should be dotted lines to represent that, but due to the scaling, those are actually smashed in here down at the bottom. But in other examples, you might see a dotted red line right along here or right along here that would show me whether I am, was above or below that tipping point. So those are some different characteristics to keep in mind when you are looking at the statistics histogram. Some additional benefits that can be found in there. Okay, so for this next demo, I want to talk about something called live query profile. So for that, I'm going to grab a different command off of a little cheat sheet I happen to have off to the side, and I'm going to go up to the command text and replace this with just a simple select star from all sold inventory. Before I do that, I am going to resize my windows intentionally just because I want to show you what happens when we execute a long-running T-SQL statement, such as this guy here. So I'm going to click on Get Actual Plan. And with something that's really cool here, let me do this, and I'll do a little bit of native zooming. Is that I can actually visually see where we are spending our time. So as of right now, we're actually spending our time down here in the inventory operator, as I can see here. So we're gathering a whole bunch of data out of here. Oh, now look, we've changed. We've made a little bit more progress here. So now there's a lot of activity going on with this hash match between sales history and then the operators down here that also relate to this reference of the inventory table. So this is actually a really cool way to see the workflow of what's going on behind the scenes as your query is actually executing over the course of time. So again, we call this live query profile. For what it's worth, when I click on Get Actual Plan, I happen to have the option with or without live query profile. So this is essentially us keeping an extra close tabs as to everything that's going on. So that way you can monitor in this little progress tab everything that's happening. Now this isn't all that useful if you happen to have statements that run really, really fast, but in the case of this particular select statement, this is something that's going to take many, many, many minutes to complete. So this is a cool way that I can sit here and watch and see where's my bottleneck, what's going on here, right? So in this case, this is actually a select star from a nested view, VW all sold inventory. So I'm going to stop this. And sometimes, I need to, I need some help unraveling this view because if I zoom out of this execution plan, I see that I have a whole heck of a lot of things that are going on here, right? So, this is there's a lot of different operators here. It's not just something that's going against one simple construct. So one thing that can definitely help you out is the join diagram down here. And this can help you visualize exactly everything that's actually going on here, including self joins back to itself potentially. So this way I can now see the true relationships between the underlying tables in the course of my statement as opposed to everything that's been abstracted away thanks to that particular view. So make use of that join diagram to see all the tables that are actually in play in a given query. So now what I'd like to do is a demo around user-defined functions. So first of all, I'm going to go up to command text. I'm going to replace this with a different piece of code here now. and let's run get actual plan. So for this, we've just executed, this piece of code here, but as you can see, there's a couple of scalar user-defined functions. And as we know with scalar user-defined functions, they're repeated row by agonizing row per the total number of records that are actually returned by the select statement. For the purposes of time, I've just done a select top 20 to limit this to only 20 results. But now, if I look at the full call stack here, I can see all of the individual executions of different pieces of code. But the thing is, I'm not sure which pieces of code pertain to what. So there's a really cool optional column that I'm going to add via the column chooser called object name. I'm going to bring this in here. I'll do a little column resizing. Let's do that. Get rid of that. And now when I zoom in, now I see that these two statements are part of that first scalar user-defined function. These two are part of the second, and so on and so forth. So I can see easily now how each of these executions repeat one after another, after another, after another. To further better visualize this, you can always look at the start time and end times. Now, granted, most of these all happen very, very quickly, so it's really, really tight. But you might imagine being able to see this with longer scalar user-defined functions to see exactly which ones are hitting and how they're repeating one after another. Another cool thing is that we're showing you the true reads and writes that are occurring behind the scenes as well. This statement happens to be so fast that I'm not sure if it actually uses CPU or not. But one interesting thing is this. With the we used get actual plan, and when I actually click on one of the select statements, we actually don't have a query plan for it. That's because just like in Management Studio, if I used get actual execution plan in Management Studio, we can't actually see that because of the way SQL Server essentially hides, or I'm not exactly sure of the internals of it, but essentially it's running it in its own like session or child thread or something like that. So essentially, we can't get at the underlying execution plans. The only way we can see what the execution plans would look like for these user-defined functions is to use get estimated plan. And again, this is exactly the same inside Management Studio if you were to do this over here, over there as well. So now that I've done that, we have the net profit and the net commission. Note that because we're inside the estimated execution plan, I don't have the parent object names because we don't have the full call stack. But now when I come down here, well, let me resize the windows. I apologize. Now we can see, for example, this first statement, this is the shape of the plan diagram. So now I can actually clearly see what's all going on inside this execution plan for this scalar user-defined function. So this is a case where you're going to have to make use of both get estimated and get actual in order to cross-reference back and forth what's really going on behind the scenes. One of the drawbacks of these little functions here. Okay. So what I want to do next is start wrapping up with my final demo. And this is going to be kind of like my workflow for the diagnostic process is essentially what it boils down to. So I happen to have this stored procedure here called get sales history by customer. Let's get actual plan on this guy here and execute that. Oh, it's already running. There we go. Okay, so the first thing I typically do is I'll sift through all of the different result values just to see if anything actually jumps out. One of the things that is particularly useful are the different percentage columns, like estimated I/O costs, estimated CPU costs, and so on, and just the overall cost. What these percentages represent are not like CPU usage percentage, like we use 60% of the CPU, 40% of the CPU. Rather, it is showing you the percentage of a given record for the entire result set. So for example, whatever this statement here happens to represent 5% of the entire result set here. So typically what I would do is I would quickly skim through this to see what my top cost statements happen to be. Or of course, remember, I can sort by any one of these guys. So I'm simply going to sort by the estimated cost column first to see, are there any statements up here that happen to be that big, ginormous statement that's killing everything else? In this case, no. I happen to see a whole bunch of entries that are 5% in this case. And in this case, this may actually be a situation where instead of just having that one major statement that's completely blowing out the performance of this store procedure, this could be a whole bunch of different smaller statements that are adding up. So it's the sum of its totals as opposed to anything else. So to better understand that, let me just give you a quick overview of what this store procedure is doing. Remember, we had resorted by total cost, or the estimated cost, I should say. So what I'm going to do is I'm going to click on the Statements tab up here and reset sorting. You remember that quick tip from earlier. So now let me do a little bit of zoom in here. So what this piece of code is actually doing is it's doing a whole bunch of looping, where I'm going to grab 3 different random customer IDs per loop execution. And then when I go down, let's see, right here. So then after I grab those 3 different unique customer IDs, I'm going to do a select insert into blah, 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 where customer ID is equal to 1, union all, select the same select statement for where customer ID is equal to customer ID 2 and then customer ID 3. So it's a bit of a contrived demo code, yes, I fully admit it, or basically we're grabbing 3 different customers at random and then doing that as one singleton insert into one insert statement. And this is going on repeatedly, so we're looping through this particular bit of code. So that's one reason why we're seeing, a whole bunch of different insert statements where the estimated cost happens to be 5%. But this is me, if I'm just troubleshooting this piece of code, I'm looking for these types of patterns. So I'm going to want to sort my different statements by different data points so that I can get a better sense of, is there something from a pattern perspective that's going on here, as opposed to, again, that single massive crazy statement. So one other thing I might look for is to see if I had any unnecessary unbalanced parallelism. So let's come back up to the top in the column chooser, and I'm just going to throw in our parallel operations column here. Do we have any non-zero values in this particular case? No, doesn't look like it at all. A quick way, if I don't want to necessarily scroll through anything, is just click on the filter button and we will show you the discrete values that are also in play here as well. So in this case, 0 is the only possibility. So I know that none of these statements actually went parallel, so that's not a bad thing at all. But if I had found any of those, maybe I would jump to those and go through the process that I did earlier of checking the plan tree, see if I had any crazy unbalanced parallelism, and if I did, maybe I'll chase down the statistics histogram inside index analysis to take a further look to see whether my stats are completely off that cause the unbalanced parallelism. So if I go back to that insert statement and go down to the plan diagram, I can look at the root here, and hey, we do have that little warning symbol on this guy. So this is a case where, I may want to take a look at that and see what's going on here. Come on, I had the tooltip a moment ago. Fantastic. So what I wanted the tooltip was that the warnings are actually showing me that I have multiple implicit conversions. I also have an excessive memory grant here. Now, I don't really care about this memory grant in this case because these values are relatively small and trivial. It's just being highlighted because it's a huge percentage difference. But regardless, I'm seeing that we happen to have 3 implicit conversions. But remember, this is a union of 3 select statements that are all effectively identical. So this is a place where I'm going to want to double check the underlying data types of these two tables: sales summary heap VIN and inventory and flat VIN, to see if there's anything that's potentially hindering me there. So that's one thing I can start looking into. Another thing that I'll always double check is whether I happen to have any missing index recommendations or anything else like that. So, I might peruse up top in the summaries here, and while I don't have missing index recommendations, I do see my other friend, the key lookup here. And whenever I see key lookups, to me, that's another bit of low-hanging fruit that I could potentially do something about. So let's go find one of those key lookup operations. So I have an index seek against the sales history right here. So let's take a look at index analysis to kind of get a better sense of what's happening here. So in this example, we're using the sales history customer ID non-clustered index here. We have the pink columns here that's actually showing me that these two extra data points, the inventory ID and transaction date, could be really useful to help fully cover this particular query. In the case of this execution, I can see very clearly down here. Actually, if I let me rescale all of this so that we can see the tipping point. There we go. My tipping point range is just about 5,000 to 6,500. However, in this case, my quality rows are 9, estimated to actual 5. I'm well below that tipping point, which is why we see the index seek and key lookup operation combination here. But nonetheless, because this is one of those high volume queries and maybe something that's running my workload on a frequent basis, this might be a case where I want to make an adjustment to this non-clustered index and add in 2 more included columns. Note that there was already an included column here, whatever this guy was. It is sales history ID. So I'm now going to include these other 2 columns that are being requested by this particular query. Let's do this. We'll execute this guy here, because we're going to live dangerously and play and make modifications in production, of course. I'm going to get actual plan once again, and then we'll go find one of our insert statements and then take a look at how performance changed on that. Okay, here we go. It's one of our insert statements. Let me select one of my clustered index seeks. Now you may notice, or if you're thinking to yourself, Andy, there could be completely different variations, and you could be exposed to parameter sniffing. That's absolutely true. But this is where looking at that statistics histogram for each of the individual executions could potentially help you out, because maybe you have a customer ID that had a whole heck of a lot of values as opposed to some of these guys that had next to none. But we're working off of a cached execution plan here, right? So, this is a case where like parameter sniffing could sneak in and burn us here. So this is why having access to the statistics histogram to be able to quickly check this information can be very valuable. So let's go back here. So I do still have some key lookups, but instead of 6, I now have 3. Now I'm going to guess that's due to key lookups against a different construct. Yeah, I have key lookups against inventory and flat, which we did not resolve. We were addressing the key lookups on the sales history table. So we've at least gotten rid of that. And notice that in this example, it looks like I actually have a missing index recommendation, so I can further improve this on the customer guy here, so I can continue to make more and more improvements. Now, by the way, I totally forgot to check, actually, let's first look at the table IO tab. I haven't really talked about that. Did we decrease or increase our overall table IO usage? Well, in this execution, we did about a total of 21,000 logical reads. I don't remember what we did before because I forgot to check it, but this is the history tab to the rescue. I can go back to the prior execution, and now let's look at the table IO. 40,000 instead of 21,000. So this is an example where I cut my IO nearly in half just by eliminating those key lookups, by making that modification to that non-clustered index. So this is a really good, clear example of eliminating those key lookup operations can really reduce your overall IO needs. On the other hand, do notice this. My total elapsed time up here, 9 seconds, 10 seconds, we actually increased. What's going on here, Andy? Why did this possibly happen? And this is where we're going to want to potentially look into other things that are going on. For example, we investigated, bad parallelism, but I see just, maybe I want to go deal with the other non-clustered the other key lookup operations, or I maybe want to now sort all of my different statements by duration and look at the longer running statements and see what I can shave off from there. Or are we in a case where, you know what, 9 or 10 seconds is about the best we're ever going to get out of this because of the underlying work and all the different looping that we're doing? Can I refactor this to no longer loop? But assuming that we're stuck with the loops, this may be the best that we got because we do have that looping construct and it's something that takes a lot of time. But again, hopefully you get a better sense of how I might go about looking at one of these pieces of code when I'm, cracking something open for the very first time. I'm going to be looking at a lot of these different data points that we happen to have available. I'm going to be looking for these different usual suspects. And depending on what I find, I might start pursuing down other different data points as a result. Okay? So that's just kind of an example of my workflow whenever I'm working within Plan Explorer and I want to start tuning a piece of code and how I might continue going down that path. All right, back to the slides. So I'd like to leave you with some parting thoughts. Hopefully, after the time we've just spent together, you have a better appreciation of some of the advanced capabilities within Plan Explorer. I encourage you to explore the column chooser to see what else is out there as far as the discrete data points that are available to you in your execution plans. I encourage you to play with custom layouts so that way you can visualize all the information the way you want to see it. And I encourage you to start leveraging Plan Explorer as a performance tuning environment, not a development environment, but a perf tuning environment. Think of it in that regards. And hopefully you'll gain even better benefit and greater speed when it comes to start perf tuning your code the more and more you use it. So I encourage you to give it a shot and let me know what you think. And with that, thank you so much for joining me today. I hope you enjoyed this presentation. I would love to hear any feedback you may have about this presentation. My contact information is all in the bottom there. And of course, there's a reference once again to my GitHub where the PE session file that I've been using is all going to be posted. So you don't even need my database. You can follow along pretty much everything that I've just done using the PE session file. So in either case, thank you so much. Once again, SQLBits 2020. I thank you so much for having me. I miss you all. Stay well. Bye bye.